my screen, right?
Yeah,
Perfect. Let me just check one thing here. Oops. Okay, perfect. Wait, so what exactly do you guys see on the screen? Just the slides, right?
applications of pins. Yeah, that's
Okay,
it.
perfect. Okay. So I'll get started then. So my name is Aja. I'm a master's student at Western University. Essentially, right now I'm going to present a physics-informed neural network approach to solving the two-dimensional Helmholtz PDE. It's mainly like an application of how pins work. I think we've already had a presentation on, I guess, the theory of pins, so we'll go more on the application side, right? What's interesting about the Helmholtz equation is that it appears in like wave propagation problems such as acoustics, electromagnetics, and steady-state vibration. And what's interesting is that classical numerical methods like finite elements often require like meshing and they become like very expensive for highly oscillatory solutions. So the goal here is to approximate a solution directly within a neural network by enforcing the governing PDE and boundary conditions during training. So I guess the contents are they're pretty straightforward, right? I'll just go over the problem statement and the goal. I'll show you how all the data is created for the training and testing, how the pin is constructed and things like that, and essentially how the training loop works and evaluation metrics. And then I'll conclude with why this PDE makes solving it so difficult and why, pins are very useful in solving such problems. So I guess I'll start off with, I guess, the problem statement, right? We can essentially consider the second dimensional Helmholtz PDE on the square domain. So if we have like omega equal to, I guess you could say like -1, comma 1 cross -1, comma 1, right? We essentially have a square like this. And we can define the partial differential equation as this right here, which is essentially del of u of x comma y plus k squared of u of x comma y equals the forcing term f of x comma y. Um, in this equation, essentially, we have u of x comma y. This is the unknown scalar field, right? K is like a fixed wave number. And like I said before, f of x comma y, this is a forcing term in the PDE. The triangle, I guess you call it del, this is like the Laplacian, right? This is essentially going to be, I guess you could say like the derivatives, right? So u of x, derivative like this, and then we need it for y as well, right? So it's partial of like this, and then partial y squared like that. So that's essentially what this represents right here. The goal is essentially to approximate a solution using the PD residual and boundary constraints, right? Obviously, the main difficulty is that the solutions are very oscillatory, and this PD contains many second derivatives, which is like hard to compute. And it makes optimization very stiff within the neural network. So how do we construct the training and testing data, right? So it's actually kind of like a backwards solution, well, like a backwards methodology, you could say. We will actually start off with a manufactured solution, which is this function right here. This is the true solution of the PDE. And essentially, to measure the accuracy precisely, we use this manufactured solution approach instead of solving the PDE with an unknown ground truth. We essentially prescribe this exact analytical solution, right? Um, so in reality, you have numbers like A1 and then A2, right? In the real world, they can be any real numbers. But when we train our PDE, we'll have them as any integer, right? That will be very easy in the code to compute and things like that. Um, Once we have this function, we will derive the forcing term, like I mentioned before, f of x comma y, so that this u of x comma y satisfies the Helmholtz equation exactly. And then this lets us test the compute error on a dense grid without using labeled training data, right? So this is our data. We essentially create data using this function right here. Here I have I guess you could say like a plot of what this function looks like. So any function that exists within, I guess you could say, this family of functions would satisfy our solution. Only question is, what is that function going to be, right? It just needs to fit within this realm right here, and then that's it, right? So once we have our function, right, from the manufactured solution, we need to derive the forcing term analytically. That means we need to compute the second derivatives first, right? Because we have our data sampler constructs f as, I guess, the combination of second derivatives plus the scalar times u, right? So we will compute the second derivatives. So I guess like another way of saying this is like u like this, and then x squared, right, is equal to this, and then similarly for y, right? These would be the second derivatives, and then we can substitute them back into the original PDE. So this is, I guess, the substitution, right? By substitution, we sub them back into the original PDE, and it gives us, I guess you could say this identity right here, right? Well, it's like it's this, and then these two are identical to each other. So with this forcing term, the manufactured solution satisfies the EE throughout our, I guess you could say our boundary omega, right? Like we defined before. The square boundary that is, right, of all the boundary and initial conditions. So BC and IC, right? So this is to satisfy the boundary. And on the topic of boundary conditions, we will, I guess, impose the Dirichlet boundary conditions on, I guess you could call it like the partial omega. We'll just call it the boundary condition here. And this essentially means that, I guess, u of x comma y is equal to like an arbitrary function g of x comma y on the boundary. And essentially for this manufactured solution, since like sine of like, I guess, any integer n, or sine of x times pi equals 0 for like any random integer, or yeah, I have it right here, right? On the boundary values for like x plus or minus equals 1. And the same thing for y plus or minus equals 1, right? They equal 0 because sine is like oscillatory, right? Like this. It kind of it satisfies our boundary conditions, right? So it means that the boundary condition simplifies to homogeneous on Dirichlet conditions, meaning that all the boundary values will be 0. And this essentially matches the training loss implementation that penalizes directly on the boundary. And thus these boundary conditions are like constrained, and they're enforced through the boundary loss term during the training. It's very, very important when we are training our pin, because we essentially have two, I guess you could say, two loss functions, one on the boundary and one on the physics itself. Next, this is, I guess you could say, the pin approximation space and network mapping, right? So in a standard pin, we approximate the unknown solution using a neural network, right? In this case, we can call the neural network u sub delta of x comma y, right? So this is our neural network. And then these are parameterized by the weights delta, right? So these would be the weights of the neural network. The network will essentially map the spatial coordinates to the scalar field. So from 2 dimensions to 1, right? And instead of like using labeled pairs, we train, I guess you could say, we train the weights delta by minimizing how much u sub delta violates the PDE in boundary conditions, right? So this is essentially how, I guess you could say, this is our neural network, right? And here we have like our standard like MLP of like, I guess you could say, 2 inputs. We have our hidden layers here, and then a single output, right? So this would be our solution, which is essentially going to be, I believe, L2 error, right? But yeah, essentially we're trying to minimize the boundary mismatch. That's essentially it with this. Now, once we have our data and once we have our neural network, right? We want to, I guess, normalize the inputs and then derivative scaling, right? This essentially improves the optimization stability, and we normalize inputs using the sample mean and standard deviation. So I guess I have a normalized like X, right? Because our neural network is evaluated on it's on like X hat, comma Y hat, right? With respect to X, comma Y are inputs, right? Oops. It means we need to normalize this, right? And we do this using the chain rule, right? So for one dimension, this would be the chain rule, and then this is the equivalence right here, right? The same scaling will actually apply to y hat as well. So I don't have this here, but like it's essentially the same formula. So y minus mu and then standard deviation. So this happens to both x and y, and these scaling factors are essential so that the residual corresponds to the physical partial differential equation. And we have autograd derivatives are divided by obviously this for each differentiation step. Depending on the type of PD, this can be pretty expensive, but this is why it's very important to like optimize our neural networks efficiently, and we know like what kind of data we're using with, right, or we're utilizing for training and testing, right? Now for the physics residual construction by automatic differentiation, we'll define the PD residual for the neural network approximation as this, I guess, function right here. I'm not going to say that all. And then the terms, let's see, in two dimensions, right? The terms of u u sub u sub theta of the second derivative of x and then of y as well. They're computed using automatic differentiation in PyTorch, right? These will give us the exact derivatives of the network output with respect to the inputs. And then this essentially helps us enforce r sub theta is equivalent to 0, right? At many of the interior points, and ensures that the learned solution satisfies the Helmholtz equation across the domain, right? So as I said before, we have a square domain, boundary conditions on each corner in the interior points, right? Now, on that topic, the boundary versus interior collocation points is our sampling strategy essentially, right? So the training will use 2 points, right? So one is going to be the boundary points on the square, like I said before, on each corner. And then we have omega, right, which is our interior, which is inside, right? This is going to be, so the square is going to be used to enforce the Dirichlet conditions, whereas the interior is to enforce the PDE residual, right? Typically, we will use a larger batch size for the interior points than the boundary points because the PDE constraint governs like the global structure of the solution, right? So this is very important when we construct our data. And then for the neural network itself, we have our loss functions. So we actually have two loss functions in this, right? The first is the total objective, is the boundary loss right here. And then we have the PDE loss right here, right? This one is essentially enforcing like the physics, right? Like I said before, right? As long as it's as close to 0 as possible, it's good. And this is just going to be whether or not our solution fits within the boundary, right, of the PD. So these would be the known points, and then this would be the physics. And then we can essentially combine the two loss functions and have, like this, okay, total loss right here, right? So L of theta. So there's actually two different methods of training this, right? And this really depends on the PDE. One would be like the standard atom optimization, which uses like I guess the combination of the two loss functions. So actually, I'll do that again. So the total loss, right? So L1 plus L2, as I showed in this equation right here, right? The other solution, right? We can actually have two separate loss functions and just use them as like I guess 2 points like this, and then we look at them independently, right? So we can essentially train using standard stochastic optimization like Atom, using the combined loss. But in some pins, like Helmholtz, like for example, it is common for the physics and boundary gradients to have like different magnitudes and conflicting directions, right? So I guess the multi-objective essentially addresses this when we treat them as two different losses, and then we apply like a conflict-aware, I guess, multi-objective update um, called dual cone gradient descent. And then the goal is to, I guess, reduce the destructive interference between the objective and to improve the training stability. Dual cone gradient descent is actually a very famous paper. Well, it's not that famous actually, but it was published in Europe, I think, in 2024 in Vancouver. So it's like I guess you could say it's like state of the art right now. So any like research that comes out of like pins, the expectation is it is built off of this paper right here. Now, how do we, I guess, see if our results are correct, right? So we, for our evaluation metric, we will essentially evaluate over the dense grid like omega, and we'll report the relative L2 error, right? This is done after training. So I guess we'll define the test grid right here of all the points that we've generated. And since we know the exact solution, we can essentially just report the error, right? So the difference between the 2 points. So I guess if we have like, I guess this is a very simplification. If we have like a known solution, and then these would be the points from our pin, right? We can just, I guess, calculate the distance between the known points and the generated points from our pin. And I guess we could just compute, I guess, via the predict function, right? And evaluate the best checkpoint by the lowest training loss right here. And then I'll just conclude with why, the just general pin details and why this equation of the Helmholtz PDE is so difficult, right? So like I mentioned before, the Helmholtz equation can produce very like highly oscillatory solutions, right? And neural networks often learn low frequency components earlier than the high frequency components, and sometimes referred to as spectral bias, right? It's a very, very big problem in pins. Second, derivatives in the residual amplify approximation errors. This can make the optimization very, very stiff, right? And then normalization, careful sampling, and multi-objective optimization can improve training behavior for this PDE. And essentially, I have some possible remedies that we can use, right? So better loss weighting, adaptive sampling, frequency-aware architectures, creating better loss functions, so on and so forth, right? So I guess to conclude, this is like how a pin would solve a PDE such as Helmholtz by representing the solution as a neural network and training it to satisfy the physics and boundary conditions. This approach is pretty like it's very fast, right? When I tried it on my computer, I was able to solve the PDE within like 10 minutes. And it's really good because it avoids like mesh generation, and it can solve the PD without any labeled solution data, right? We only use one function, as I showed before, and all our training and testing data comes from there, right? So yeah, using that manufactured solution provides a clear benchmark, and relative L2 errors plus the residual plot confirm the correctness and accuracy of our given solution. So this concludes my presentation. I'm open to any questions that you guys may have.
What do you mean by manufactured solution?
Okay, so the manufactured solution here. So we know that so the PDE is already solved, right? We're not solving a PDE that like is unknown. It's not like the Einstein equations, or what's it called? The wave equation, right? We already know the solution to this PDE. We
Okay.
just need to define a function here and then find just any like random integers a1 and a2 so that it kind of fits our known solution correctly. This is a pretty big challenge, right? Because how are you going to find a1 and a2 precisely, right? So this would be like our base, and then I guess you can just compute all the derivatives from there using Python. I can share you all the code files after this presentation if you guys want to see some implementation on this. But yeah, we essentially start with a manufactured solution for our training and testing data, and then we go on from there.
Okay. So there can be a case where you don't know the manufactured solution, right? What happens in that case?
Yeah, in that case, it'd be very difficult to solve the pin. I don't think this approach would even work if you don't have a manufactured solution. So if you're trying to solve, I guess you could say like the Einstein equations, this wouldn't really be a technique to use. So you kind of need to have I mean, I guess what you could do is you could use like real world data, right? Rather than
Mm,
just using a function, if you have like sensors and things like that, and just collect the data points like that, you can use like that, but it wouldn't be as accurate. So this is still like a very primitive like approach to doing things. But it does lay groundwork for, I guess, future work with like actual sensors in the real world and things like that.
okay. And one other question that I had was, do you think like any time series can be thought of as a PDE or some kind of, where you can use something like this in any time series data?
Time series. In theory, it could work, but pins are like really pins really work well under, I guess you could say, like low data environments and like high dimensions. Time series usually has pretty like low number of dimensions. I think you can use like a standard neural
Yes.
network
Yes.
for
So
time series.
for example, you take any biosignal that you uh, from your body, right?
Uh,
Like PPG
uh,
signals or EEG signals.
yeah, I guess.
So
It depends on the dimensionality of the data then, right? If you can represent it as a PDE, right? I guess you could, but if you can't, then a standard neural network approach, like a CNN or something, or not CNN, just regular neural network, right, would be sufficient. But that's a very good point. If you could represent in multiple dimensions in a way that a solution exists within a partial differential equation, you might be able to. But otherwise, you might not go down this entire rabbit hole and just use the standard neural network. But no, that's a very good question. For
yeah,
sure.
because in that case, like in the case of biosignals, you also don't know the manufactured solution, but you do know
That's
that
true.
it's a wave, it's following some kind of a pattern, or there is
Uh,
something there. So maybe it
that's
can
true.
be
Maybe.
represented.
Maybe, yeah, yeah. As long as you can put it as a PE, I don't see any problem. But that's a good point.
Mhm. Okay. Anyone else has any question? Yeah, I think all of us don't have any background in pins, so that's
Uh,
why we don't have any questions.
Yeah, it was a good presentation, but I guess, yeah, it was
uh,
difficult to understand, but yeah, it was good. Yeah.
yeah, I
Yeah,
can
somehow, yeah. Yeah, go
take all
ahead.
if you guys want, I'll provide all the code files, and if you guys want to run it
Yeah,
on your like
that
Yeah,
would be
computers,
great.
if you can like give us a very small tutorial on how would you write pins and stuff, it would be
yeah, yeah,
great. It would be
sure, yeah, I'll send you all the neural network code and the data, the samplers, and everything.
that
I
would
can
be
give a
awesome.
tutorial on like how I'm trying to improve this as well. We're trying to use like LLMs to create these functions right here, right? Which is very
Uh-huh.
interesting. So that's what we're
Mhm.
trying to present in um, I think ICML in January.
Mhm.
So we'll see how that works. Fingers crossed.
Okay. Okay. Is it the same work that log data you were working on, like the same thing or different?
Oh no, this is different. That's another project.
Okay.
Yeah, yeah, yeah.
Okay. Fair
Whole
enough.
different project.
Mhm.
I saw
Okay.
a
Okay.
Thank
hand
you.
up
Yeah,
from
it was
Uday.
really good.
You have a question?
No.
Hi. So this was a great presentation. Thanks for this. I just wanted to ask that, so you've been working on synthetic data generation a lot, right?
Yeah.
So is that also mostly related to PDEs, or have you worked on other types of data, like maybe time series or something?
Or like my research in general.
Yeah, yeah.
Okay, yeah, yeah. It's a diverse domain of like data. So one of them was like tabular data.
Okay.
So like regular database style data, right? Where it was important that there was like numerical constraints within the data, and then data would like relate with each other, right? So for example, I'll give like for heart data, for example, right? Let's say you have a blood pressure, it must fit within a certain range, right?
Right.
Age must fit within a certain range, and then I guess you could say like I'm not sure exactly the characteristics, but each column needs to like relate with each other, and if any of these constraints are violated, we would need to check that. So that was one thing I worked on, generating tabular data such that it was like accurate and highly diverse and things like that. Um, that paper we still haven't been able to publish because the reviewers are a pain in the ass, but it is what it is, right? And then the
Okay.
second paper for synthetic data is on like JSON, like textual data itself.
Okay.
So that's just seeing like if the text is diverse. We use a lot of like NLP, like natural language processing techniques to verify the solution, to verify whether the data is correct and diverse and things like that. And
Yeah.
this is just purely text, whereas the tabular one is like mixed with numerical and categorical. This one we actually published in MS, so I need to present or prepare the camera ready soon. And then what's the next one? I had another one on like what's it called? Like actual like real like visual data, like computer vision stuff, right?
Okay.
Where
Okay.
we had like adversarial attacks on like road signs and things like that.
Mm-hmm.
That one is under review for CVPR, I think. So we'll see how that goes. And then now we
Okay.
have this one, which I'm trying to create data for like physics functions, like this one right here.
Yeah.
And then I think the log one, right? That one is still under works as well. I'm not sure where I'm gonna submit that to. But yeah, my research on synthetic data is like pretty diverse. But essentially I'm trying to create solutions for data constrained environments such as pins and things like that, and make them easy for researchers to utilize and things like that. Yeah.
Yeah. No, that's amazing. So, uh, another question is, so for example, if I want to generate synthetic data for like, physiological time series signals, then do you have any insights on how, we can go about it?
For time series. So actually, the first work that I worked on, we did explore a bit of time series, right?
Hmm.
What we found was that so when you use an LLM to synthesize data, right? Um, we find that like with many iterations, LLMs will tend to hallucinate and they'll try to like fabricate results and really
Right.
memorize solutions, right? Data privacy and memorization is very important here, right? What
Yeah.
we found was that we need to have a way to evaluate the data precisely, such that it's correct, right? So for time series, for example, since we know that, there needs to be a relation as time moves on. That's the whole
Yeah.
thing with time series. It's important that you identify evaluation metrics, right? Whether that would
Right.
be like some basic stats like KL divergence or whatever, right?
Hmm.
You need to be able to compute these kind of numbers between the real and synthetic data sets. And then you need to be able to translate that into like a text-based feedback to the LM so that the LM can understand, because LMs cannot just understand just standard like numbers, right?
Right.
Once you identify the metrics to evaluate in a way to and a mechanism to translate that into text, you have a pretty solid foundation for synthesizing any kind of data, whether it's time series, tabular, JSON, even physics, right? Anything. So that would be my advice.
Mm. Nice.
Mhm.
Thanks. But I think these signals are so complicated. RS is working with EEG. I'm working with PPG that you don't really understand these signals even with
Yeah,
complicated neural networks. You don't know
exactly.
what
Yeah.
features are there, what are meaningful features. So it will be
Right.
pretty complicated, I think. But thanks.
No, especially like as we like these real world problems are very like high dimensional, many different variables come into play. So, synthetic data plays a very big role, and also designing our network architectures as well. So very crucial.
Yeah, exactly. So a problem we are facing is subject level separation. So there is a lot of inter-individual variability in these signals. So if we can somehow generate new types of signals that we might get from new individuals, then that would be very helpful in training these models.
Right?
But
Lots of
yeah,
work, yeah.
yeah.
Very interesting. For sure.
One point that I would have is that if you're able to generate new data, doesn't that already mean that you have a good enough representation for that, which
Yes,
you can use
exactly.
to solve anything?
Yeah, yeah.
Yeah,
Yeah.
essentially, yeah. It's like a circular problem.
Yeah.
It is. So the chicken and the egg, essentially.
Mhm. Okay. Does anybody else have a question? Okay. So thank you, Aja.
No
And
worries.
Yeah, thank you for nice
Thank you so
conversation.
and
much.
yeah,